Hey everybody, it is 5 o'clock Tuesday and time for some Calc 3. Um, First off, guys, did a great job uploading the solutions to the forum for last time. So that's how we're going to do it from here on out. I'm no longer taking any submissions on the stuff we've already done. So whatever we work on tonight, we're going to work on the 11.6 worksheet. That'll be the next one that you guys upload. I made a small tweak to the schedule for later this week. I originally had, I think, 2 sections for Thursday. I switched it to only have 1 for Thursday because I want to make sure we have enough time for 11.6. It's a really good section. It's one of the funner ones, I think, where we really start to get an opportunity to use some of the math that we've been doing and some problem solving. And I just wasn't sure how much time we'd have for 12.1 today, but there's a few things I want to make sure we do in 12.1. So what we're going to do today is we're going to start with 11.6. I'm going to highlight a few things about lines and planes, give it an opportunity for any questions that we want to go over. And then we're going to do a couple problems in groups on the 11.6 worksheet. And then I'm going to save a little bit of time at the end because I do want to talk a little bit about 12.1. Depending on how it goes in the group work, we'll kind of figure out how much time we have left. I'm going to save at least 15 minutes at the end to talk about 12.1. If we have more time, great. If we don't, we'll save 15 minutes at a minimum. And then whatever we don't talk about on today, we'll have some time on Thursday. Okay. So I wanted to, so there was just a couple small tweaks. So if you notice any difference in due dates, when you look in the calendar, that's where it came in. Didn't change anything for today. We're still going to do 11.6 and we'll start 12.1 by the end of class. All right. So let's get into 11.6, lines and planes. I want to highlight a few things, like always, and opportunity to ask some questions as well. So first thing we're going to talk about with lines is the relationship between parametric equations and vectors. All right. So hopefully, you've at least had some experience with parametric equations to this point. And it's essentially when our not that I'm aware of. Sorry, guys, I got to go on to 11.6. Could you maybe email me that question about 11.4? I don't have time to look at it right now. Okay, so we're looking at the relationship between parametric equations and vectors. And parametric equations are when we assign separate equations to each variable. And it's going to allow us to create a lot of cool shapes. And right now we're just talking about linear functions. So basically straight lines. So in 2D, we would have 2, one for the x and one for the y. And t is what we call the parameter. All right, so this would be a line that goes through the point x0, y0, and it has slopes of a and b in the x and y directions respectively. All right, now you can do a parameter elimination on this to get it into a function just in terms of x and y. But I'm not worried about that right now. But there's some nice properties that dealing with parametric equations of lines gives us. For example, we know that it goes through the point x0, y0, and it's parallel to the vector AB. All right. So it makes it very easy to find the equation of a line just given a point and a vector that the line is parallel to. So in 3D, we add on the z component. And this is a line that goes through the point x0, y0, z0, and slopes of a, b, and c in that direction. Now, one thing I want to point out, this does give us a line, okay? When we do parametric equations, not a plane. We're going to talk about planes here in a little bit, but this would actually just give us a one-dimensional line. And CalcPlot 3D can do parametric equations. I already have it open, so let me just show you. Under Select, we're not doing parametric surfaces yet. That's going to be something we do later this semester. When you see space curve, that's parametric equations. So we're just talking about a line right now. We'll talk about some pretty cool space curves later in class, but let's say we wanted a line that goes through the point 1, 0, 1. So 1 plus 2t. So what do we, 1, 0 minus 1t, and 1 plus 1t. All right. Now we just get a line segment, and see what I wanted to show you. Two things. Two reasons for me to do this. One, I wanted to show you how to put in parametric equations into the 3D plotter. Two, notice we don't get a plane. We actually get a line in 3 space. And it's actually technically a line segment because it's only going from 0 to 2 pi. Anytime you're doing parametric equations, you'll always have limits on your parameter. Now we can make this have a negative part, and you can see that extends our line segment. But it's something I want you to get used to. And like I said, we're going to talk about that a little more when we talk about 12.1 later. But one of the things, a couple of the problems on the worksheet for 11.6 do ask you to plot the line. And so you can do that with the Calc 3D plotter. So, once again, when we have a linear function in parametric equations, or a line, I should say, in parametric equations, it'll have this form. So this is a line going through the point x0, y0, z0 with slopes of a, b, and c, or we could say parallel to the vector a, b, c. What this does is it allows us to write up these line functions of the line in terms of vectors. And we'll see that not just now, but later this semester. Vectors are a really powerful tool for organizing these things. Okay. So we're talking about linear functions today. So there was talking about linear functions in terms of parametric equations. Those make lines. Now, this is nothing new. Linear functions in 2D. So if we're in slope-intercept form, we have y equals mx plus b, where m is the slope, b is what we call the y-intercept, and m is the change in y over change in x. A lot of times we see the y1 minus y0 over x1 minus x0. And we get a graph of a straight line. Well, now we're adding in that third dimension. So this is what you guys were seeing in the videos. So we have to think about what it means to be linear in 3 dimensions. So now a linear function in that same slope-intercept form would look like mx plus ny plus c. So now, not only do we have a slope in the x direction, so if we keep y fixed, z is going to change by m. So basically, we can say that our m is our change in z with respect to our change in x. Change in output with respect to change in input, if we were to hold y constant. N, very similarly, is now our change in z with respect to a change in y. So now we have slopes in 2 different directions, and this is what creates this function. Now, as you guys saw in the video, this in the videos, excuse me, this creates a plane in 3D. So a linear function in 2D is a line. A linear function in 3D is a plane. So if you imagine walking around on a tilted plane, the slope may not always be the same. So if you walk in a direction parallel to the x-axis, you'll always be walking with the same slope. And if you walk in a direction parallel to the y-axis, you'll be walking with the same slope. And that's why we have those constant ratios, our m and our n. Now, there's going to be, just like with linear functions in 2D, right? We have slope-intercept form, we have point-slope form, and general form. We have all three of those for a plane as well. So this would be more like our point-slope form. And this could be really useful because now all I need is mn and a point that it goes through. So we're going to see today, there's a lot of cool ways to come up with the equation of a plane. And so what form we decide to use, well, it depends on what we're trying to do. And there's also a lot of cool properties that come out of linear functions. So here's the linear function 7 minus 3x plus 2y. And I'm just going to give you a couple minutes just to take a look at any patterns you might notice. All right. So just look at the table. And these are the x's going across the top. These are the y's going down the vertical. And notice what happens with the outputs. When I move across horizontally, as I move left to right, what's happening with my outputs? What kind of pattern do we see there? Yep, output is decreasing, and like Ryan said, it's going down by 3 each time. Well, look at what our slope in the x direction was. It was -3. Not in, yep, good call, Cooper. Look at what's happening in the y direction. Up 2, up 2, up 2. Again, not a coincidence. Now this is also pretty cool. Look at the diagonal. 7, 6, 5, 4, 4, 3, 2, 9, 8, 7, 11, 10. What's happening as we move across diagonally? It's going down 1. And if we think about combining those slopes, -3 and +2, that's a -1. So once again, none of these characteristics are coincidental. They're all coming from our function. So everything ties together really nicely. So just like with 2D, we like linear functions in 3D because they're very easy to work with. They have constant rates of change. So we're gonna spend this first section dealing with planes, lines, and things having to do with planes and lines. It's true for all linear functions. So just like in 2D, for the function to be linear, x and y can't have any exponents. They have to have exponents of 1. Now, we could be missing one of them. You know, it could be just 7 minus 2y or 7 minus 3x. Maybe this term is missing. We could be missing x or y. That would still be a linear function, would still have all the nice patterns, but we can't have an x squared in there or a square root of y, because then it's not linear, just like in 2D. And once we have that, we have the constant rate of change, which makes all these patterns consistent. All right. This next part is actually pretty cool. We talked a little bit about, I alluded to this last week. We were foreshadowing a little bit. We talked about normal vectors. So if you have a normal vector to a plane, that vector is perpendicular to that plane. Okay? Now, suppose we have some plane. This here is the uppercase pi, which passes, and we're just using it for plane. Sometimes you'll see that in math. which passes through the point x, y, z, and has a normal vector a, b, c. All right. Now we're going to start by identifying another point in the plane, x0, y0, z0. All right, so let's kind of sketch out what's going on here. So this is going to be, let's give it an angle. So this is going to be our plane here, sitting out here in 3D. Oops. And we've got some normal vector. Could be anywhere in the plane, but let's just put it right here. So that's going to be our normal vector to the plane. Okay, now we have some point x, y, z in the plane. Now here's what I'm going to do, and let me know if you have questions about it, because this is really cool how this works out. I'm just going to go ahead and say x, y, z is this point right here, because it's going to make my picture look nicer. I can put x, y, z anywhere, but I can also move the normal vector anywhere. All I care is that the normal vector is perpendicular. So that's going to be our x, y, z. All right. Now we're going to pick some other point in the plane, and we'll call this x0, y0, z0. This is any point that lies in our plane. Now, we know how to find a vector between these 2 points. All right? And it doesn't matter which direction the vector goes, but because of the way I wrote it up, I'm going to cheat a little bit. I'm going to make the vector go this way. All right? So that vector there is going to be the vector x0 minus x. These would be its coordinates, y0 minus y, and z0 minus z. All right, so that's just this vector between the 2 points. Now, what do I know about the relationship between these 2 vectors? If this is the normal vector, and it's perpendicular to the plane, well, then what's its relationship to this purple vector, which is between 2 points in the plane? Call this guy, we'll call him V. They're also going to be perpendicular. Yep. They're also going to be perpendicular, and because they're perpendicular, their dot product is going to equal 0. All right. Now, I'm going to take those 2 things, and because their dot product is 0, if this is my normal vector, so if we say, okay, we're just going to say our normal vector has the components A, B, and C, and we dot this guy with this guy, check out what we get. We get the equation of a plane. So times y minus y0 plus c times z minus z0. This is what's known as point normal form of a plane. Guys, this will work for any plane. So all we need to find the equation of a plane is the normal vector and any point in the plane. We don't even have to do the dot product. You can actually go straight to the formula because I can plug in the components A, B, and C of the normal vector, and we can plug in the point in the plane. So the 2 things you'll always need to find the equation of a, excuse me, let me rephrase that. 2 things that we know will always find the equation of a plane is a normal vector and a point that goes through it. Now, the reason that's valuable is that, say we're trying to find the equation of a plane. Well, then we know if we can get to a vector that's normal to the plane and a point in the plane, we can find the equation of a plane. So now, instead of thinking of it as some long problem of trying to get to a plane, we can think of it as kind of a subset problem, meaning, hey, if I can get the normal vector to the plane and a point in it, I know I can find the plane. And we're going to look at an example of this in just a second here. But I want to pause there. Questions about that? And I know I sound like a broken record because, oh, sorry, Cooper.
Oh, I was just wondering, so how do you find the point on the plane? Like, what technique do you use? Because I remember the video showed something, but I don't remember exactly what they did to find that extra point, your x0, y0, z0 point.
So, in a lot of cases, we'll be given that point. So it'll be, say, find the plane that goes through a particular point. Because if you think back to doing linear functions back in 2D, we could always find a linear function with a slope of 2, but there's an infinite amount of them. Eventually, we needed to know a point that it goes through, kind of like an anchor. So most problems, you'll have a point that you're going to be trying to go through.
Okay, thank you.
In some of the problems on the videos, where it was like a parametric, they just set t equal to 0 and use that point.
Yeah, and that goes, yeah, thanks, Daniel. And that goes back to what we were talking about earlier. If we have, I'll scroll back real quick. If we have if our line is given in this form, this is a line that goes through x0, y0, z0. So that would be our point in the plane. So setting those to 0 would also be a way, if we're not given a point, of getting a point. All right. So, one thing I'll always bring up, because you're going to see it, we do come up with a lot of different formulas in this class. Remember, I'm not asking you to memorize formulas. You'll have the note cards for the exams. You'll have your notes for quizzes. If this is something that, you're worried about not being able to remember, which is totally fine, make it a piece on your note card, okay? All right, so now that we have this, let's talk about how we can use some of the things that we've done before to find the equation of a plane. So here's one using the cross product. So any three non-collinear points, so the word non-collinear means that those 3 points don't lie on a line. Because if the 3 points all lie on the same line, we have an infinite number of planes that go through them. But any 3 non-collinear points determine a plane. That's just a fact. So let's talk about how we could do this knowing what we know now. So I'll just kind of sketch what's going to happen here. You guys, I know you saw it in the videos, but I just want to make it intuitive. That's not what I want to do. Sorry. So if we have 3 non-collinear points just out in 3 space, well, what we can do, and we want the equation of the plane that goes through them. Now we're already given we're given 3 points that are in the plane, but doing what we did last time with the cross product, we can find a vector we can find a vector through those two. We can find a vector through those two. And remember what our goal is. We wanted a normal vector to the plane. So the cross product, as we know, will give us a vector that is perpendicular to the plane that those two lie in. And so there is our normal vector. We could use the components of that normal vector along with any of those 3 points. We only need one of them, along with our point normal form, to get the equation of a plane. So we're combining what we did last time with what we've learned this time about point normal form to get the equation of a plane. It's actually pretty slick. Now, like we talked about before, you know, always be careful with your calculations. There's a lot of places to make errors in a problem like this. But now, given any 3 non-collinear points, we can find a plane going through them. We find 2 vectors between any 2 of the points, do the cross product between those to get the normal vector, and then we have our point normal form of the plane. All right. So the next part, this is all going to be stuff you guys saw in the video, but I wanted to just give you some intuition from where it comes from. But it's going to be things that we can do using the math that we have learned over the past couple weeks. And this is going to be some more formulas. But again, I stress, don't worry about memorizing formulas, worry about knowing how and when to use them. All right. Distance between a line and a point. So given some line and some point P that's not on the line, we need to find the distance. So first we find a vector between P and any point. So that Q is any point on the line. So, you know, Cooper had asked, you know, how you find a point. You find any point that satisfies your line. You can start by setting one of your variables to 0 and then finding the other 1 or 2, depending on if you're 2D or 3D. And then we're basically just doing a vector projection. We talked about this a little bit last time. We didn't, not last time, probably 2 classes ago. The vector projection finds the component of PQ that is perpendicular, because we're doing a projection in the direction of a normal vector. So we're doing the component of PQ that is perpendicular to the line, therefore it'll have the shortest distance. Okay? You're going to see this theme a lot. And this is where this dot product comes in. It boils down to, if we have the vector between the 2 points and a normal vector, this is all we need to do. We're dividing by the magnitude of the normal vector to make the normal vector a unit vector. All right. So these are going to be just knowing when to apply these formulas. We've done dot product, we've done magnitude. So it's just knowing when to do them. Distance between 2 non-parallel lines in 3D. It's going to be all about finding a line that's perpendicular to both of them. So you find a point on each. We find U, which is parallel to one of the lines, and V, which is parallel to the other, because then their cross product is perpendicular to both lines. So once again, we'll do a vector projection of PQ in the direction of our normal vector. So it looks like almost the same formula. Notice there's an extra step before we apply the formula. And in this case, we have to calculate the normal vector with the U cross V. So that's if you have 2 non-parallel lines. If 2 lines are parallel, they're always the same distance apart. So there's no minimum or maximum distance. And finally, between a point and a plane, this is going to be similar to between a point and a line. So we can do something very similar. You find that PQ between our point P and any point in the plane, and then we're going to do the vector projection of the vector PQ in the direction of N. So it always ends up looking like the same formula because it is. It's just there's small little differences. This is between a point and a plane, where the other one was between a point and a line. And the second one was between 2 non-parallel lines. So you may not get a chance to try these out all these out today on the worksheet, but you definitely will in the homework. And again, do not worry about memorizing the formula. Pay attention on how you're using it. Okay, two more things that I want to talk about. And again, these were in the videos. So if you're trying to find the angle between a line and a plane that intersects it, we know how to find the normal vector of a plane. It's basically just all the coefficients. That's just going in the opposite direction. So if I go back here on our whiteboard, right, if we have the equation of a plane in any form, ABC is our normal vector, right? So that would give us our normal vector. And once we have the normal vector, we know how to find the vector in the direction of a line by doing a vector projection. So then we can find the angle between those two vectors. So we would have this vector, because we know the equation of the plane, that would give us the normal vector. This is our line. Well, we know how to get a vector that is parallel to our line. We know how to do the angle between two vectors back from dot product. That would give us this angle. So we need the complementary angle, and that's why it's pi over 2 minus the angle, or 90 degrees minus the angle if you're in degrees. All right. So you can see how the stuff in 11.6 builds on what we've been doing. It's actually really cool. Lastly is the angle between two planes. So if you have two planes that intersect, there's going to be an angle between them. Well, it turns out the angle between two planes is equal to the angle between their normal vectors. So you find the two normal vectors, and then you're finding the angle between two vectors. Now, one thing I'll mention on this, there's two angles, right? There's this acute angle, and then there's this obtuse angle. The problem will tell you which angle to find. It'll say find the acute, the angle in between 0 and 180, or 0 and pi. It'll give you a range, or it'll say find either of the angles, and both of them will be acceptable, or find both of the angles. But once you have one of them, the other is just the supplementary angle that both add up to 180 degrees. So we're building on all the stuff we've been doing over the past couple of weeks, and now we actually get to start to apply it in some problem solving. So that was what I wanted to talk to you about with lines and planes. So now I want to cut you guys loose to try some. Like I said, I want to reserve at least 15 minutes for 12.1. I'm going to give each group 2 problems, except for one group is going to only have 1 problem because it has 2 parts. The worksheets are all at the top of chat. And but before I break into groups, any questions?
How do we find the angle between two vectors again?
Remember, we have those 2 definitions of the dot product, the algebraic and the geometric.
Mm-hmm.
You set those equal to each other.
Mm-hmm.
And theta you won't know because we'll have the vectors in component form.
Yeah.
And so you'll do the dot product with the algebraic definition. You'll have a value. You'll calculate the magnitudes of the 2 vectors, and those will be multiplied by your cosine of theta. And then you'll solve for theta from there.
Is this just the vector A dot with vector B over the
Got it. Over the 2
magnitudes.
Divided by the 2 magnitudes.
Yeah, and then arc cosine that.
You got it.
Okay, all right.
You got it. Perfect. The angle between 2 planes might be necessary if you need the angle between 2 planes. So it doesn't give you anything bigger than that. It just gives you the relationship of how they intersect. So in a real world context, you could imagine wanting to know if your plane is a ramp. You could imagine wanting to know the angle there. You can model the angle of your plane with a vector, or vice versa. You could use the angle to get the equation of the plane to create the ramp in AutoCAD or something like that. So that's the way I think of an angle of two planes. I think of it in terms of ramps. So how steep or shallow is the ramp? Okay, guys, I want to get you guys going on this. We'll have up till about 6:15, and I'll be pulling you back. If you guys are done early, feel free to move on to the 12.1 worksheet and play around with it a little bit. I'll put this in here, and then I'll also throw it. I'll also put it out once you guys are in groups. Doesn't really help you when you don't know which group you're in. All right. Okay. Rooms are open, and don't worry, I'll put those problems in the rooms too. I'll broadcast them, so you'll have them there as well. So you should have an invite over to your rooms. We got a good 35 minutes to work on these problems. Let's see how we do. All right, guys, welcome back. One thing I'll mention real quick, just in case it ever happens, if you ever don't get through your problem or problems in the group work, because I know sometimes it gets cut a little short just because we have a lot to try and cover. Remember, you can always, if you got a couple steps left, you can always finish it up after class before you post. Remember, you have the answer key on the worksheet, and you do have access to the solutions in more, okay? So, you know, I just want to make sure that what you post in the forum is the solution from, you know, you get to a chance to get to the final ending part, okay? All right. They're not due today. I would like to get the take-home problems into the forum before our next class meeting. So the take-home problems from 11.6, you should have those posted by Thursday afternoon. Okay. So yeah, you don't have to rush into it tonight. You know, everybody's got other things they got to do. Okay, we only got a few minutes left. I did want to talk about something in 12.1. We'll finish it up on Thursday. So you learned about vector value functions. We're going to spend more time on the vector valued functions on Thursday and doing some calculus with them. So we'll finally 3 weeks in, we'll get to start doing some derivatives. But a vector valued function really is just the parametric equations we've been seeing. We just write it up as a vector, okay? So our x of t or y of t or z of t make up the three components of our vector. It really just gives a way of organizing our parametric equations and leverages what we know about vectors. Here's what I want to do with you guys now is look at some plots, because some of you guys might want to work on the worksheet for 12.1 between now and Thursday. And we might not have as much time to do this part on Thursday. So I wanted to do a little bit of this now. And if we have time on Thursday, we'll do a little more. All right, so we know that the graph of cosine and sine as a parametric functions from 0 to 2 pi makes a circle. All right, so again, now these are our space curves. And for right now, we're going to put a 0 in there. And what it does is it creates a circle of radius 1 in the xy plane. You can see it there. Nothing new, guys. That's straight out of trig. Here's where it'll start to get interesting, because we're going to add in that third dimension. Right now, I've got it at 0. But we can start to do some really cool stuff. If I change the z, let's say to 1, notice what happens. It's still the same circle. It's no longer in the xy plane. So this is some of the cool stuff we'll be able to do with space curves. And basically messing around with basic parametric equations. Here's something else I want to show you. What happens if we let that z vary? So we'll call it t. Now when we set z to be a constant, all the z values were forced to be 1. Now z is going to vary just as cosine and sine will. And remember we talked about the t range. So we're going to go to 0 to 2 pi. And look at what we get. Now I need to change my axes a little bit so you can see a little bit better what this actually is. It makes something that looks kind of like a slinky. So let's get up to 2 pi. Oops. And what we get is a helix. And I want to point out a couple things about this helix. And that is, notice that it starts here and does one complete winding and ends up here with a height of 2 pi. One of the things that we'll be trying to do is how do we modify this so either we get more windings or maybe we wanted to end or start at a particular point. So check this out. If I change cosine and sine, if I change their period to be 2, I get double the windings. So now I've got 2 windings. This helix has a height of 2 pi and still has the radius of 1. What if we wanted to have a height of 10? Well, then I've got to multiply this guy by a linear factor. And normally if we had more time, we'd spend more time investigating this, but due to time constraints, if we multiply by 10 and divide by 2 pi, sorry. 2 pi. Oh, sorry, yeah. Now it'll have a height of 10. So if I raise my Z max to 10, now I have a height of 10. I still have exactly 2 windings because I'm going from 0 to 2 pi, but I basically cut my period in half by putting the 2 in there. And by changing that linear function there, I know it's going to have a height of 10. I'm showing you this because this is going to be one of the things, hopefully we have time to play with this on Thursday in class, but if not, I'm going to want to try and get you guys to play around with these graphs a little bit, outside of class, because it's really cool some of the stuff you can create. Here's something that we can do that's really cool. If I put a t in front of the sine and cosine, remember what, before it was just, well, actually, let's do this before we put a t, so you can see how all this works. All right. Now, if I put a 2 just in front of the cosine, and now it's kind of hard to see what happened unless we look downwards. Check out that oval, because now we've doubled the radius in the x direction, but we didn't change it in the y direction. So modifying this value in front of the sine and the cosine changed the radius of our helix. So something we can do that also is really cool, we can make that radius vary, and we get what's called a conical helix. So this would be a conical helix that does 2 windings, has a base radius or max radius of 2 pi, because we know that t is going from 0 to 2 pi. So when t is at its maximum, those would be 2 pi's in there. But you can see the conical shape. It gets bigger and bigger. And these are fun to play with. If we increase the period, it actually starts to look really cool. We can see the cone shape. It starts to look a little bit like a tornado. Let's really amp that up a little bit. Whoops, maybe not that much. And so what I'm doing is kind of playing around with my conical helix. Now it's not able to render it quite round because of the number of steps. Let's see, turn those steps up. Now you can see it gets a little bit smoother. Now this is a conical helix that's going to do 20 windings and have a height of 10. So one thing I want to point out, I'm not guessing on the height. I'm not guessing on how big the radius of the base of this conical helix is. I know because of my equations. I'm going through this with you guys because this is a problem that you'll get on the take-home problems, is how do you make a conical helix or a helix of a certain radius with a certain number of windings? It comes from playing around with your parametric equations and also your interval. So I wanted to make sure I went through a helix and a conical helix with you, just in case, because you have done the lessons for 12.1. So if between today and Thursday, if anybody wants to play around, I wanted you to know how to do it in Calc Plot 3D. Do you know which factor affects the height? It all comes from trig, and if you're not sure, it comes from playing with it. So X and Y, because this thing is circular in the XY direction, let's go back to just a regular helix. It'll make it easier to see some of this stuff. So X and Y are what are making the shape in the XY plane. So if you look straight down, I'll do it as best I can, we still just have that circle of radius 1. That's because if I eliminate Z, I've got a circle of radius 1 from the cosine and sine. If I want a bigger radius, well, that comes from multiplying sine and cosine by whatever we want the radius to be. The windings, well, they come from the period of sine and cosine. So if you remember from your graphs of trig functions, that's this factor here. Remember, it was the b, and then you do the period by doing 2 pi over b. And so that tells me how many windings I get, because notice, if I don't do any, if I leave that value at 1, whoops, wrong thing, I get exactly 1 winding. In other words, I'm starting here out at 2, and I'm out at 2. You can see it if we look straight down. See how we get see how we get the circle there if we look straight down? Starts where it ends. So 1 winding is a period of 0 to 2 pi. So to get more windings without increasing the height, we change the period. Lastly, to change the height, well, Z is the height of this thing because it's climbing up the Z axis. So anything I do to my Z function is going to change the height based off of this interval from 0 to 2 pi. Now, one thing about parametric equations, there's an infinite amount of ways to do your parametric equations to get the same graphs, because I can also change my range on T and then make corresponding changes in my equations. And that's going to be something that, that's going to be something that you guys can play around with. All right, so we only have a minute left. Like I said, I wanted to show you that because I wanted you guys to know how to put in no, I can't think of the name, the space curves, which are basically the plots of these vector valued functions. All right. And from the, you can use the PowerPoint to get some of the basic equations. I'll be posting the video of today's lessons if you want to look at any of the things that I did. Because on Thursday, we're going to do some calculus with vector valued functions. And then whatever time we have after we finish up the worksheet, we'll do the same thing we did today, except I might actually leave you guys in groups to play with these the Calc Plot 3D, because that way you guys can try it. You know, we've talked about it before. The only way to get this stuff down is to do it. And so I want to make sure you guys are getting some opportunities to play with the graphs as well. Okay, guys, we are at 6:30. So the take-home problems, they count as part of the take-home problems will count as part of the exams. So the midterm take-home problems are 5% of the overall grade. The final take-home problems are 5% of the overall grade. So they're 1/5 of the midterm and final, respectively. And we should, let me double check one thing on the calendar. Yeah, first take-home problem is up today. So let me show you guys something. So when you guys go into course content, the midterm take-home problems folder is now there. And you've got your midterm take-home problem from Module 1. Guys, you can use any resource you want to do take-home problems. And in fact, I encourage you to. You've got an in-class exam where you're going to have to do things by hand. So by all means, use Wolfram Alpha, Symbolab, all those. They're due the same day as the midterm. It's on the calendar, guys. All the due dates for these are on the calendar. There's some submission guidelines here. your submission must be done as a single PDF with your solutions in order. And if you use Wolfram Alpha to say calculate a cross product, just do a screenshot of that little piece of what you entered into Wolfram Alpha, put it into a Word doc along with your solution, and then you can save it as a PDF, okay? There's a video in here that gives some suggestions on how to do that. So you now have access to the first take-home problem. You can start working on it tonight if you like. You do not have to. They are not due until the midterm, which is still over a month away. But I just wanted to show you this, guys. So make sure you take a look at this. Make sure you look at the first midterm take-home problem. Guys, one thing I will say, these are exam problems. I cannot answer questions that are about these problems specifically because they are exam problems. I can answer clarification questions. And also, you cannot post about exam problems in the forum. You can post about similar problems from the homework, the worksheets, totally fine. But because they are exam problems, please do not post about them in the forum, all right? Okay. Yes, once we've covered the topic, I bring up the take-home problems so that you guys can do them. So the module 3 take-home problems you'll get before the end of module 3 because the topics will have cut for them will have started to cover before that. Other questions?
Could you start keeping the videos up for like the ones you post before lecture? Can you start keeping them up over the due date? Because I'll watch the videos, but I want to go back to them, and I kind of don't remember how to find them. So is there a way you could do that?
Are you talking about the video lessons that you do before class, Garrett?
Yes.
Just use a late pass to, just use a late pass to reopen them. It won't affect your grade in any way. And you got plenty of late passes. So because they have a due date and because they're worth points, that's why a late pass has to be used to reopen them. Okay. But yeah, just use a late pass, and that way you can get back to them anytime you want. And if for any reason you do run out of late passes, just shoot me an email, and I'll make sure you got plenty more. But you should have plenty.
All right, thank you.
Yeah, no problem. I do want you to have access to those lessons, absolutely.
I have 11,000 late passes.
Yeah, I tried to be excessive this time, so I think you guys will be fine. But if somehow something happens and you run out, just let me know. Guys, there are things in this class I want you to work on, but there are definitely things I do not want you to be concerned about, and late passes is definitely one I don't want you to be concerned about. Getting back into the lessons, I don't want you to be concerned about. Opening up the homework after due dates, I don't want you to be concerned about. All right? Other questions? And I apologize for going over as always, but you guys did great today. Don't forget to post your solutions by Thursday afternoon. And Adrian, I remember you had a question about one of the solutions. If you don't mind, send me an email about that so I can take a look, okay?
Sure thing.
Thanks.
Thank you.
Whew. All right, guys, good job today. As always, guys, remember, you can always email me if you need help. If you got questions on homework, worksheets, you have the forum, you have all the online tutoring, so check out the tutoring resources. So don't ever wait to ask questions. I've seen some good stuff in my other courses in the forum. That sharing helps everybody. So post, and just don't forget to post your work. And I'll post the video tonight of today's class.
Have a nice night, Professor.
You too. Thanks, guys.
No, go ahead and go to the other store.